Hello. It's 13th of February 2024. I just felt like recording what I'm reading now. So today I spent time reading these things. Basically, I'm reading conformal field theory, as you know, in 2 dimensions, in fact. And today I started reading about operator product expansions. Operator product expansions. So what are those? Well, I won't go into them. I don't want to. But yeah, it's basically an expansion of the operators in terms of other operators regular at z equals to w, and it has the complex singular part, probably it might have. So and it's basically an expansion within the correlation functions of product of operators. So we computed. I've gone through the calculations for the free boson, free fermion, and the ghost system. Free boson involved a explicit path integral computation, which was actually not done here, but it was a part of the second chapter, I suppose. So I need to learn how to do that, and then and then we computed these correlation functions, the derivatives of fields, correlation functions of the derivatives of the fields, and then so that you can evaluate your energy momentum tensor, and in a holomorphic form you have clear definitions, and you compute the operator product expansion of the EM tensor on itself, and also on the derivative of the field. So you evaluate this correlation function of between two EM tensors at two different points, obviously. For the bosonic, for the fermion and the ghost system, you end up with a form different from how OPs for primary fields look like, which are given in this form, 5.71. You don't see other z minus w bars. So there's one z minus w and two second part of z minus w, but other terms are not there. But it's up to regular terms. There are other regular terms, but there are no singular terms. But if you see for the bosonic part, you end up with this factor, half over z minus w power 4. So you note this factor, which is the anomalous term in the primary fields. So they don't actually transform like primary fields. And then you also look at the fermionic system, Majorana fermion, with this action given bilinear. This is the bilinear that we're considering here, and you do the same procedure, but here you got to apply some tricks. Even in the above case, okay, not really, but okay, still. There's a way to evaluate this path integral, I guess, which involves some Gaussian integrals in fermionic systems, even Grassmann variables. There's a specific form which you want to bring the action into, and then you can write your correlation function in terms of this form, and you can solve this. Okay, so there is also another way you can do this via the equation of motions, which you basically do in the basically the green functions, or basically the canonical way, I guess. but there is also a pathological way to this, which I need to look at this chapter 2 to evaluate this actually. Okay, I will do that later, but we also have same procedures. You find the OPs of your fields and the EM tensor. So yep. Apparently we don't consider TZ bar and TZ bar C components. There is some subtlety to it, I suppose. I will have to figure that out as well. And then the key thing is that you end up with another similar. Okay, you sort of get the conformal dimension for the psi field, which is half, and then there's when you write the TZ and psi TZ and psi OP. I will go through this in my notes. This time, interestingly, I will start taking them. So I have installed Vim. I want to try Vim out. The powerful keyboard only sort of text editor. I've spent so many hours since yesterday evening or so on that, installing all the packages and stuff, figuring out Vim and LaTeX. Basically, figuring out Vim and LaTeX inside Vim. LaTeX is not something new anyway, but yeah. So you end up conformal dimension of the scalar field. Also, you can guess it, just this thing, right? And scalar field, the derivative of scalar field. Okay, and scalar field has no conformal dimension, of course. It has no spin. It's no conformal. It's no scaling dimension, so it has a zero conformal dimension. But the derivative of phi apparently has a h equals to 1, which kind of makes sense, I guess. Yeah. Okay. So yeah. Okay. So TZ. Okay. This. Okay. Yeah. You're basically comparing all those forms with this. Okay. 5.71 is sort of primary field. Okay, the EM tensor times the product of EM tensor and your field. How do they transform? This is how it is. The expansion of them. Sorry. So you do the same with the fermion, Maranello fermion, and then you end up with a h equals to half. So the conformal dimension of half, the psi is a half conformal dimension of field, and then you do this. There is an anomalous term again. It is a dw, right? Which you will which is 1/4 by z minus w power 4. So we move to the ghost system. We get the same thing again. Ghost system is apparently a Jacobian of some string theoretic functional integral, I guess. So anyway, you end up with another anomalous term with this time the constant is -13. So things are sort of similar in the sense that there's a sort of central charge c by 2c, and the anomalous term has a c by 2 factor there, and there is a real nice connection between the central charge and okay, so okay, Okay, so this is, you sort of expect this factor actually from considering both from single function where you can actually evaluate the this residue at sorry, not residue but the fourth order Polka residue, if you call it. The coefficient, you see, the single function has this factor of c by 2, and moreover the symmetries say that it has to drop by z power 4, right? So it sort of fits in that there is a term of this form if it's not a quasi-primary field with conformal dimension h equals to 2. These things I'll again go understand them with more depth or a bird eye view and a big picture sort of and things when I'm writing about them. But yeah, these are interesting stuff. And there's an interesting example. The central charge is somehow an extensive measure of the number of degrees of freedom of the system, because when you add two theories, in the sense you start from two different actions, you end up with the two different EM tensors which you get added into the total EM tensor, and the associated central charge also gets added up. So that's the claim. So the statement is that the central charge is somehow an extensive measure of the number of degrees of freedom of the system. The fermionic is half and the bosons are 1. And for the ghost system there is a possibility of minus 13 and minus 2, I suppose. Sorry, minus 26 and minus 2, I guess. And so we sort of now generalize this. You consider a conformal the conformal word identity and evaluate the variation, then you exponentiate this and you expand your so basically Z to W mapping, how your do you want to know how your EM tensor actually transforms, right? So it does not transform like a primary field, but it transforms some different way. Now you use the conformal word identity, which is a general word identity. That doesn't need to be applied on primary fields only. That was the sort of discussion what happened in that previous section. So you consider the variation of this T at W with respect to holomorphic variation. It has to be because it's conformal transformation, so in 2 dimensions, and you exponentiate this. This is a very non-trivial calculation that even they admitted and sort of provided a way to see this. So you sort of arrive at this expression of the transformed energy momentum tensor with a central charge appearing next to the term called the Schwarzian derivative. It's a very non-trivial expression again for the Schwarzian derivative, and infinitesimally this you can see how this definition sort of fits into the conformal word identity. I guess that's a trivial calculation here, which I will of course go through and do it in the while I'm noting things. So yeah, sort of end up, but finite in a finite transformation. How do you realize it? Well, one way is to see that this actually satisfies when you go to Z. When you move. Sorry. So you confirm this by sort of going through the Z to W, W to U mapping, which should coincide with the Z to U directly, right? So this Schwarzian derivative should sort of match the Z to U and Z to W and W to U things, artifacts. So apparently they do, and in fact, the Schwarzian derivative of the global conformal map vanishes. So your T becomes primary field if your conformal transformations are global. Is that the statement? Is that statement right? Wait. This needs to be so, for Tz is a quasi-primary field. In fact, it can be shown that Gaussian derivative is the only possible addition to the tensor transformation law that can satisfy the group property 5.130 and vanishes for global conformal transformations. This is a very interesting fact. Now, instead of providing a long and technical proof of this last statement, we shall derive the whole Gaussian derivative transformation of the EM tensor through a free boson representation. So you consider the free boson EM tensor, and you already know that the del z phi z transforms in the conformal dimension of 1, and go through these explicit calculations. So this is a normal ordered product, but I suppose it's a normal ordered product. Yep. This is a normal ordered product between the derivatives of phi, which is expressed in terms of the time ordered plus which is basically the sum of product of that with these two derivatives and also the correlation function. Okay, so normal ordered in normal ordered, yeah. Okay, yeah. Okay, how does normal ordered make sense if you don't expand your operators into harmonic oscillator, the modes of harmonic oscillator modes? But yeah, this is something again, this is another subtlety that I have to look at. Of course, definitely. So, and since phi has a conformal dimension 0, okay, so the same thing, now you expand this, all the mass, you sort of end up with the Gaussian derivative. Okay. And the physical meaning of the C is remarkable. It's known as a conformal anomaly, and it is related to a soft breaking of conformal symmetry by introduction of macroscopic scale in the system. So the statement of the physicists being physicists, they don't describe what exactly this means, just sort of give you a feel for it with some connections or stuff. So to make the statement more specific, we consider a general conformal field theory living on a whole complex plane, and we map this theory on a cylinder of silicon. So your Z to W mapping is a whole complex plane to a more cylindrical form with a natural log of Z mapping. Okay, I will go through this, of course, but it's a very statistical system. There is a which I did not understand it quite well. This is basically the central charge term, which sort of matches with the vacuum correlation function of the theory, non-zero vacuum energy density in the cylinder. So these sort of transformations give you the vacuum energy density in the cylinder, Casimir energy proportional to the Casimir energy. Now we start relating it to the statistical system where you have a free energy which coincides with the connected functional W. I don't know what that means. I'll go through the terminology. Yeah, this is a sort of calculation showing that these two are related, free energy and the non-zero vacuum energy density of the cylindrical EM tensor. Basically, one where you are mapped to from the whole plane coordinates. Now, but there is also another connection, another physical significance of the central charge. Central charge also arises when a conformal field theory is defined on a curved two-dimensional manifold, which is exciting. So when you consider a conformal field theory on an arbitrary manifold, not just a flat metric one, and also not just a zero Ricci tensor on the space. So the curvature introduces a macroscopic scale in the system. What does this mean? So there is some macroscopic scale in the system. So R is R a macroscopic scale in the system. So sort of just get the feel of it, but don't quite understand it yet. Yeah. So and the expectation value of the trace of the EM tensor in this new arbitrary manifold CFT, this CFT on arbitrary manifold is proportional to both the curvature R and the central charge C. So instead of vanishing again, this is related to some curvatures, to some scale of the theory, to some macroscopic scale of the theory. This quantum breaking of scale invariance is called the trace anomaly. The proof of 5.144 is not simple and is given in appendix 5.8 for the free boson, although the argument may be generalized to other systems. So, the motivation for this session is to read the trace anomaly. How, when you consider a CFT on an arbitrary two-dimensional manifold, you sort of introduce a scale into the system, macroscopic scale into the system, and your T mean mu, the correlation function, your new EM tensor, the correlation function is non-zero. Why was it first zero in the first? Why was it zero in the first place? I guess they're assuming okay, basically vacuum energy density is in the field, okay, you have vacuum expectation of the fields, which is just the correlation function phi, basically the 1 by z path integral d phi e power minus s of phi and phi itself, and phi itself. Similarly, you can define a vacuum energy density. These correlation functions are basically the vacuum energy, vacuum expectation value. So vacuum expectation value of the very EM tensor gives you the energy density, right? So energy density on the plane, sort of you sort of expect it to vanish. Okay, which it doesn't in the new mapped in the new theory. Although maybe you expect it to be because it's a conformal transformation, but then there is a quantum, expect it to vanish, but as you see, it is not. One such case we'll analyze now. We call the trace anomaly for a free boson. There is a static realization of central charge too, but which I'll go through later. Good. Okay, so in the appendix we demonstrate the trace anomaly for a free boson. So the statement of the main result is to prove this, right? Yes. Yeah, this thing. We want to prove this thing. Let's go. We consider the generating functional. Okay. Yeah. Okay. Got it. This is basically the normalization factor of the expectation of the vacuum state. It's just the inner product between the vacuum in and vacuum out states that you can write in terms of the path integrals. And consider the very action. Is the action of the screw failure field theory in a background metric G mu. So write the action as integral e to x rho g mu del mu phi. So the root g comes for the invariance, the general invariance of this theory. Yeah, which is on it in the GR course, which I need to go through it again, definitely. Apparently my doors is open. Okay, so here's the action. A short notation for this is the Laplacian operator. Oh, I see. I think we even did this. So it's e to x rho g phi delta phi is rho g del mu rho g mu del mu phi. Okay. Okay, yeah. Oh, yeah. This was a very non-trivial thing that we did. Yeah, I need to go through these calculations, and I will do these calculations when I'm going to type them and everything. Definitely. Yeah. Let me just say a small aside on how things are going, because I haven't updated and talked about these things anywhere actually. I probably need to do a blog post on this, but so reading these things is non-linear. It's definitely non-linear. You go ahead, you read things, you don't understand many of the stuff, most of the stuff probably, and then you sort of note what you don't understand. First thing is that you try it, and then there are some calculations that you have to actually do, but then you can't just do the calculations right when you read them, because then you would end up calculating, and you wouldn't understand what's going on, right? And you will not be able to calculate the stuff either if you go that way, because many of the calculations are worded in a way that the front and back, and sort of the clues are given away only when you go ahead through the pages and come back. So it's, as Yogi said, it's like you read 17 times, you probably don't understand. You read it 19th time and you understand. It's very non-linear, but yeah. So sort of way I figured is to not get too stuck with the calculations. Go through them. Just in first layer is go through what's happening there. What's the main message that's happening there? And the first read is always going to be a very new thing, because you'll not appreciate it directly, but you will see the picture building up, and throughout the week I keep going back, looking at what was happening. I need to do those calculations also, right? So I will go back, I'll see those calculations, I'll understand the theory, and then I'll go ahead. But this week there were two pages which involved a lot of calculations. So yeah, there was a lot of calculation this week, but there is a big picture to everything, and it's sort of nice to go ahead, look at the calculation, look at what the theory, what they're putting forward, and then on your own you can work things out. You can connect them properly, you can do your own stuff with that. So yeah, that's how it's going on for me right now. But I am going to be critical about most of the things. I will calculate stuff. So yeah. But yeah, one thing I'm definitely not doing is I'm just cruising ahead the book. That I'm not doing at all. I'll be focusing on few pages, but with care, with trying to understand both the big picture and also noting the weird claims and weird statements, and also calculations, all that. Yeah, non-real calculations and stuff. So yeah, as of now, so this is the first read I'm going through this topic. The brief summary that I was talking about earlier was my second read of this, with all this stuff of physical meaning. And it's not on second, I guess. It's probably third or fourth read. Because when I was reading of this afternoon, I already went through them again and again. Just sort of, it's not something you decide, it's something that happens. You just go back and look at it and you form the clear picture iteration by iteration, right? So, but the trace anomaly is the first iteration of this read, so I'm going to be a little more explorative and curious sort of my approach, but yeah. So, okay. Under a local conformal transformation, the metric transforms this way, sure. And how your action changes is this, yeah, sure. Okay, sure. So then consequently the variation of the connected vacuum functional. What was the connected vacuum functional? Okay, I need to Google this. What is a connected vacuum functional? It's a connected vacuum functional. What the fuck? Like getting some random robotic vacuum cleaner stuff. Quantum field theory. Correlation functions, vacuum wave function. Connected, what the hell? Connected vacuum functional. I probably have to just search connected. This is the first time I mentioned this now. Okay, I can take this as a definition, sure. Because it's just the correlation of the, it's just a vacuum expectation value of the change in the action, right? I mean, the T mu is the correlated part, taking the correlated part of the but I don't know its significance, so that's a thing. So this is first note, sort of a deeper note to things. These are the calculations that I need to go through. This is my own baggage. The new baggage is this part of the vacuum connected vacuum function. Sure. So yep. According to the Ward identities previously derived, this variation vanishes in flat space since T mu x equals 0. This is no longer true on arbitrary manifold. Okay, Ward identity previously derived, the variation vanishes in flat space since T mu 0. Yes, so we saw that. We did see that. Did we? did we see that? We saw that in a. We consider the Schwinger function, which we took more like a T mu max and T mu 0, T sigma 0. So that's some. At x equals 0, that's 0. That was in fact something we proved. But I will reconsider this and evaluate my own understanding of the previous Ward identities. So this is again something to understand at the deeper level of what we've derived, you have to sort of look ahead. And we never showed that it's 0. It vanishes everywhere except the correlation, the contact terms, right? So okay, let's go ahead. Let's see what happens. This was the starting point of the whole anomaly trace anomaly thing, which is already we noted that it is a bit shady thing that I need to understand. We were starting with a T mu max where it is 0, and then we under a conformal transformation we will see that this is not 0, but in an arbitrary manifold we need to prove that it varies to something else. Let's see. This is no longer true on an arbitrary manifold. Okay, to see this, we define the functional measure d phi in a fashion more suited to an arbitrary metric. We proceed by analogy with integration on general manifold on dimension d. The line element, d. The line element is then ds2 is g mu dx mu, and the volume element d omega is root g dx1 to dx d. Okay, if a coordinate system can be formed such that g mu is eta mu, then rho g is 1, the integration measure simplifies accordingly. Sure. Okay. Yeah. What? Okay. Yeah. Sure. Okay. In the space of field configuration, the analog of the metric is defined in a reparameterization invariant way. What is the parentheses? Phi 1 phi 2 braces is equals to integral d to x rho g phi 1 star phi 2. Okay. Okay, so we are getting into the evaluating this function integral which we haven't plugged previously, but it's okay, I can just go through this. The integration is accordingly in the space of field configurations, the analog of the metric is defined in a reparameterization invariant way. Okay. Again we are in 2 dimensions, I suppose. Phi 1, phi 2. What are these phi 1 and phi 2? I suppose they're just fields. Okay, sorry. In the space of the fields, we have 2 fields, phi 1 and phi 2. Okay, we locally defined differently, same, whatever. And the analog of the metric. So metric is a thing that acts on the 2 sort of vectors and 2 fields or something. So phi 1 and phi 2 are those things. The metric acting on them is sort of an integral between integral of root g times phi 1 star and phi 2. Okay, then the line element is simply delta phi comma delta phi. I see. Sure, I see. Okay, the metric is defined this way. The line element is this. What about the volume element? In order to diagonalize this functional metric, we introduce a complete set of orthonormal functions phi n in such a way that phi n is delta m and Okay. And express any general field configurations is phi equals to c phi, and the line element thus reduces to delta c square. Sure. Wait, what? Okay. What? Wait, what? I see. Okay, so the way we diagonalize this, right? We sort of use a Cartesian coordinate system in this, right? The same way we're trying to write these. So the x's we are writing in the Cartesian standard coordinates. We are looking such a standard coordinates on the field of space. Sorry, the space of field configurations. So then now we are introducing a complex set of orthonormal functions phi n. These now you express your any phi in terms of these phi n's, and phi n's weighted with cn's. So your cn's are sort of the coordinates, c1, cn, so cn. These are not finite dimensional, definitely, I suppose. Yeah, I mean, well, it's mostly infinite dimensional. That's what whole problem is about. But yeah, sure. The line element thus reduces to delta cn square, and the function integration measure is the cn square. Of all possible complete sets phi n, the most useful is a set of normalized even functions of Laplacian with eigenvalues minus lambda n. Delta phi n minus lambda n phi n. The action of a configuration specified by the expansion coefficient Cn is then simply oh, that is very interesting. Okay, the action becomes this. Now your integral becomes Gaussian. You see? Let's see. Oh, and your weight function is actually connected vacuum function is this e power minus HR. I don't know if this is statistical mechanism or what. I don't know. I'll ask around. I will roll around, ask around. Sure. Okay, we're recording. Diagonalize this function metric, we introduce a complete set of coordinates. The line element is reduced of all possible metrics of complete sets fine. The most useful is this. So do you see this? Do you see how the action can be written as this? I mean, do I see this? Okay, let's go back. So this is phi delta phi. So phi you can expand in terms of c and phi n. Again, this also the same, c and phi n. बीच में delta घुसा हो. But delta phi, okay, अच्छा, the eigen functions. Okay, so lambda n phi n, and then you have lambda n बाहर आ जाएगा, and then you have the integral of phi n. Wait, phi delta phi, right? So delta phi, you're already defining your states delta phi as minus lambda n phi n. So you first expand your phi in terms of cn, you cn, and then integral d2x phi m phi n, but these are normalized to delta mn. The root g is also involved, and then this thing, but you don't have a phi star there, so which is a because China sucks, but these are normalized in this way. Okay, but I do see how the delta mn function can appear, and then you get a cn square, and then the lambda n is similar. Yeah. Sort of makes sense. The details have to be worked out. I will in the next session. Which means that the modes phi n decouple. However, all is not trivial since the eigenfunctions phi n and the lambda n depend on the background metric G mu. Definitely. The vacuum functional may be written as d Cn e power minus lambda n c square, which is pi n 2 pi for lambda n, which is basically a Gaussian integral. Which we must be cautious here since the Laplacian always has a zero mode phi 0 constant with vanishing eigenvalue. Such a mode is a source of divergence in the vacuum function. To fix this infrared problem, okay, low energies basically. To fix this infrared problem, we compactify the field phi. We assume that phi takes its values in a circle, such that values phi and phi plus a are equivalent. The circumference a can be chosen very large and taken to infinity at the end of calculation. Then the range of integration of C0 is no longer the whole real axis, but the segment 0 to a root a, where a is the area of the manifold. This follows from the normalization condition phi 0 a is 0 a phi is equals to 0, and the condition that this has to line a. The above expression of the vacuum function is then replaced by n is not 0 this time. How exactly this solves the problem? We have to go through this again. Yeah, sure. Compactify the field phi using that phi take the challenge. Okay, so all these problems is exactly being solved. How n equals non-zero is. Okay, we used to restrict in a box and find this stuff. Here we are compactifying by taking a circle instead. I guess that's the same thing. But yeah, just do it explicitly and find it now. So the connected functional becomes these things where here prime indicates that T is taken over all non-zero modes. We then use the following representation of the logarithm in order to write this. Okay, we scale t to 2 pi t. From now on, we keep what is b? Okay, there. And we scale t to equal minus 2 pi t. From now on, we keep epsilons finite and shall send it to 0 at the end of the calculation. Yeah, sure. We now perform an infinitesimal log scale transformation. Again, what connected vacuum function was sort of distribution function of this thing. Okay. So yeah, I think it's more like, sorry, it's more like you use this definition of the connected vacuum function e power minus wg, so that the w becomes actually integral of okay, anyway, let's keep on. From now on, we keep epsilon small, epsilon 100 and shall turn into 0 at the end of calculation. We now perform an infinitesimal local transformation. The variation of the metric delta g mu sigma g mu. That of Laplacian is minus sigma delta. The variation of the second term of 5.160 is this. That of trace is this. Second equality, we use the property of all non-zero eigenvalues of delta or negatives with that. Values of delta or negative, so that we may combine the two variations into a single expression. It contains the contribution of the zero mode, hence Tr prime has been replaced by Tr. To proceed, we introduce the heat kernel. Since the eigenvalues of delta can be arbitrary negative, the expression equal T delta has meaning only for T greater than or equal to 0. So that E or something negative makes sense. Equal T delta equal minus why should we for something greater than 0? In terms of this heat kernel, the variation of Wg is this. Crucial point is the short time behavior of the diagonal kernel, which can be shown to be oh my god, this is the most crucial thing. The heat kernel for the short time behavior of the heat kernel, there is number of epsilon plus 4 pi of Rx. Okay, now that's going to be our tedious calculation. This result is given in the appendix 5b. It follows that the variation is as follows. In the limit epsilon to 0, the first term seems problematic, being infinite. The origin of this dimension is assumed finite cell with manifold and has nothing to do with curvature. To fix this, we add to the original action the following 5 independent counter term. Interesting. Which is simply equal to mu a under what's a. Okay, the area of the manifold under a local schematic. For now I need to go by suitable using mu to be equal to minus 8 pi, under the local transform and the following radiation. delta S1G equals to mu delta 2x G. By suitably choosing mu to be equal to this, the variation of the counter term action S1 cancels the term this. Okay. The action, the second term in the 5.168 cannot be eliminated in the same way. Indeed, if you can add a second term, if you add a second term of the form, you will find that it is proportional to the Euler characteristic x, a topological invariant that depends only on the number of handles of the manifold. Therefore, it is invariant under local sign and cannot cancel the rest of variation. Then the equivalence of 5.149 and 5.168 implies that the trace of the energy potential does not vanish. 168 and 5.149. I see. Okay. Not vanish. Does the equivalence of the value is equals to 1 appropriate? In order to relate the trace anomaly to the central charge, figuring in the OPE of the energy tensor equivalent to the 2-point function, we proceed as follows. Use the conformal gauge, a coordinate system in which the metric tensor is diagonal, conformally related space-time. We use the conformal gauge. Interesting. Coordinate system in which the metric tensor is diagonal in 2 dimensions, it is always possible to find such a system, at least locally. In terms of the field phi, the determinant rho g and the curvature r is the local scale transformation amounts to a... Wow, this is the phi's of our very field, man. This what? Okay, I mean this needs to be proven. In 2 dimensions, it is always possible to find such a system. Since a local scale transformation amounts to a local variation of the field phi, the corresponding variation of the connected function Wg is equal to unity in the case of field. This implies that the Wg is this. The 2 terms of phi. The green function Gaussian, this is अच्छा अब एक्शन को लिखो अच्छा you use Wg itself to calculate okay Schwinger function basically the oh yeah all you have been evaluating for the OPs and all that is just the Schwinger function का OP is interesting. Without a detailed calculation, this is by now clear that Schwinger function is proportional to C, which confirms the central charge and the coefficient of trace anomaly as the one and the same thing. Interesting. Very detailed calculation, which I have to do it. Probably. Yes. Yes. I have to do it, man. Come on. Let's see. For now, I sign off. Bye bye. Good night.